Welcome back to Discrete Math. I'm Dr. Jeff Groh. Today we're going to continue talking about sets, and in particular we are going to talk about set operations. Let me define our first set operation. If A and B are sets, then the union of A and B is denoted by A union B, and A union B is by definition the set of all x such that x is in A or x is in B. So there's a significant OR statement here. In terms of a Venn diagram, if this is your universe and this is set A and this is set B, then the union is everything in either one of the two sets. For example, if A is the set 1, 2, 3, and B is the set 3, 4, 5, then A union B is 1, 2, 3, 4, 5. Note that 3 appears in each of these sets. It will appear once in the union of the two sets. Another operation is the intersection. The intersection of sets A and B is denoted by A intersect B, and here's the definition. It's the set of all x such that x lies in A and x also lies in B. So there's this significant and here. Remember, and is like this. This was or. This is intersection. This is union. They're very similar, except one of them has a little angle here and this other one is just rounded. In terms of the Venn diagram, if this is set A and this is set B, then that is A intersect B, the region of overlap. And for example, if A is 1, 2, 3, and B is 3, 4, 5, then A intersect B is the set that contains 3. Two sets are called disjoint if their intersection is empty. So disjoint sets have no points in common. If this is A and this is B, A intersect B would be the empty set. And so A and B are disjoint. As an example, suppose A is 0, 2, 4, and B is 1, 3, 5. Then A intersect B is empty, therefore A and B are disjoint. How do you determine the cardinality of the union of two sets? The basic picture, if you're trying to figure out how many elements there are in the union, if you count up the number that are in A, that's fine. If you count the number in B as well, then you've counted these twice. So you have to subtract the cardinality of the intersection. And so, in example, suppose A is 1, 2, 3. B is the set that contains 3, 4, and 5. Then the cardinality of the union, which we know is the set 1, 2, 3, 4, 5, that's cardinality is 5. That's supposed to be equal to the cardinality of A, which is 3, plus the cardinality of B, which is 3. But you have to subtract off the cardinality of the intersection. The only point in the intersection is 3, and so the intersection has a cardinality of 1. And so that checks that this formula works in this particular case. But this is the formula in general. The difference, A minus B, is the set of all x such that x is an element of A and x is not an element of B. So if this is A and this is B, when we subtract, and by the way, this is also commonly denoted with a diagonalized slash like this instead of a minus sign. I kind of like that minus sign because we're subtracting the parts in B that happen to overlap A off. The difference, A minus B, will be everything in A that is not in B. For example, if A is the set 1, 2, 3, and B is the set 3, 4, 5, then A minus B will be the set 1, 2. Let U be the universal set. This is, by the way, is a particularly bad definition. What do you mean by universal set? It's been shown, it's easy to show, that there is no such set as the set of all sets. Nonetheless, in unity with our idea about there being a universe, let's suppose we have some set A. The complement of A is a bar or a complement, and we'll define it to be everything except what is in A. So A complement will be everything that isn't inside of A. It might be better to refer to the complement of A inside of some other set, U. So that would be a valid definition in that case. As an example, let's suppose our universal set is 1, 2, 3, 4, 5. And let's let A be the set 1, 3, 5. Then A complement relative to this universal set here will be 2 and 4. There are certain set identities that you need to be aware of. First, if you take a set and intersect it with a universal set, you get A. If you take a set and take the union of that and the empty set, that also gives you A. Alternatively, if you take the union of a set with the universal set, you get the universal set. And if you intersect a set with the empty set, you of course get the empty set. Also, if you take the union of a set with itself, well, you get itself. Same thing with the intersection. And finally, if you take the complement of the complement, you end up back with A. There are also commutative and associative laws for the union and intersection. A union B gives you the same thing as B union A. A intersect B gives you the same thing as B intersect A. So there are also associative laws. A union B union C gives you the same thing as taking A union B union C. Same thing with intersections. A intersect B intersect C will be the same thing as A intersect B intersect C. We also have certain distributive laws between unions and intersections. If we have A union B intersect C, you'll get the same thing by taking A union B intersect A union C. Similarly, A intersect B union C will be A intersect B union A intersect C, like this. There are certain absorption laws as well. What's A union, the quantity A intersect B? Well, A intersect B has things that are in A and also in B, so in particular it has things that are already in A. So if you lop that on with A, all you get is A. If I take A intersection A union B, here I have everything in A or in B, but I'm intersecting that with A, I just end up with the things in A again. Finally, we have complement laws. If you take the union of a set and its complement, you get the universal set. And if you take the intersection of a set and its complement, there's no overlap, they're disjoint, and so the intersection is empty. Let's show that A intersect B complement is A complement union B complement. In our proof, we have to show this set is equal to another set. And remember, the only way to show some set A is equal to some set B is to show A is a subset of B and also B is a subset of A. So let's do this way first. We'll say let X be an element of A intersect B complement. What does that mean? That means X is not an element of A intersect B. Well, what kind of things are in A intersect B? Well, those are things that have X an element of A and X is an element of B. And we're saying that that's not the case. It is not the case that X is in A and X is in B. Well, we know what happens with a not and an and. What we get is X is not an element of A, or X is not an element of B. Well, this is an or statement, which leads us to a union. A union of what? Things not in A and also things not in B. Things not in A are things in A complement, and then the union of things not in B, that's in B complement. And so that's the end of the proof in this direction. We have to do the proof in the other direction as well. So for our proof going the other way, we'll let X lie in A complement union B complement. And what does that mean? That means X is not an element of A, or X is not an element of B. Well, that's the same thing as not X in A and X in B. X in A and X in B is A intersect B, but not means everything else outside, which is the complement. And that's the end of the proof. We can give an alternative proof that might be a little more efficient. The complement of A intersect B is the set of all X such that X is not in the intersection A intersect B. So what does that mean? That means set of all X such that it is not true that X is in A and X is in B. Well, we can distribute the not and get the set of all X such that X is not in A or X is not in B, but the or means a union. A union of what? Things not in A, that's A complement, and things not in B is B complement. In our next example, I want to prove the distributive law. A intersect B union C equals A intersect B union A intersect C. And so we'll begin with A intersect B union C and say that's the set of all X such that X is in A, intersect means and, X is in B union C. So I can put and X is in B or X is in C. So we have this and an or. So we know how those sorts of things work. That's the set of all X such that X is in A and X is in B, or X is in A and X is in C. And that's just A intersect B union A intersect C. Another way to prove set identities is by the use of membership tables. Let me give you an example. Suppose we have A, B, and C. Instead of using true and false, we're going to use ones and zeros. 1, 1, 1, 1, 0, 0, 0, 0. 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0. Now, what is B union C? They're the things either in B or in C, so it's an or statement. So we'll have 1, 1, 1, 0. 1, 1, 1, 0. Then how about A intersect B union C? Those are the things in A and in B union C. So we have an and statement here. 1, 1, 1, 0, 0, 0, 0, and 0. Has to be and. Now let's look at A intersect B A and B. That's 1, 1, 0, 0, 0, 0, 0, 0. A intersect C, A and C, 1, 0, 1, 0, 0, 0, 0, 0. And then finally, A intersect B union A intersect C. That's A intersect B or A intersect C. So it's an OR statement between these, 1, 1, 1, 0, 0, 0, 0, 0. And you can see that these tables are the same, and so we have the equality of these two statements. We can also use our identities to prove various equations. Prove that the complement of A union the quantity B intersects C is C complement union B complement intersect A complement. We'll start on the left-hand side. A union B intersect C complement. We already know that this gives us A complement intersect B intersect C complement. And that gives us A complement intersect B complement union C complement. And then by the commutativity property, we can have two applications of the commutativity property. That'll be C complement union B complement intersect A complement. What if we have a large number of sets? And we'd like to take the union or the intersection of all of them. We can write a great big U, and we'll index it as k goes from 1 to n, A sub k. That will be the same thing as A1 union A2 union all the way down to A sub n. So then how do I do intersections? Well, we have a great big intersection symbol, and we'll index that as k goes from 1 to n, A sub k, and that'll be A1 intersect, A2 intersect, and so on down the line until we get to A sub n. As an example, suppose I have sets A sub k, and they're equal to the closed interval from k to k plus 1. So for example, A3 will be the closed interval from 3 to 4. Let's take the union as k goes from 1 to 10 of these A sub k's. You can see that they will overlap at the endpoints. Those only get counted once, of course. But if we start at 1, we're starting with the interval from 1 to 2, and we end at 10, the one that goes from 10 to 11. So the union will be everything from 1 to 11. In another example, consider A sub k's to be intervals from 0 to 1 plus 1 divided by k. So you can see A sub 1 will be the open interval from 0 to 2. A sub 2 is the open interval from 0 to 3/2, and so on. What is the intersection as, let's say, k goes from 1 to 10 of these A sub k's? Well, these intervals are getting shorter and shorter. The left interval is the same for all of them. So we'll go from 0 to, but because these are getting shorter and shorter and shorter with the same left end here, the intersection will just involve the very last one, which is a 10, 1 plus a tenth. That's to 1.1. Alternatively, if we take the intersection as k goes from 1 to infinity, what happens? It keeps getting smaller and smaller, but always bigger than 1. 1 is in all of these sets. Every set of this form has 1 in it. So 1 has to be in the intersection. But if anything is bigger, eventually you'll find an n, so that 1 over n is smaller than that gap. And so the intersection now will be the half open, half closed interval from 0 to 1. How can we represent sets on a computer? Computer representations of sets. One way, we'll assume that the universal set is finite. So everything we do on a computer has to be finite. And so the universal set will be finite. And then we're going to order elements of U. We're going to write them as the first element, the second element, the third element, to the nth element. Then, if you have some set A, which consists of A2 and A5, we can write this set then as a bit string 0, 1, 0, 0, 1, 0, 0 until however many zeros we have. We put a 1 if that's in the set from the ordering that we've been placed on the universal set, and 0 if it's not in the set. As an example, suppose our universal set is 1, 2, 3, 4, and 5, and our ordering is, let's just say, A1 is 1, A2 is 2, and so on. If our set A has 1, 4, and 5, then A can be represented by 1, 0, 0, 2 and 3 are not present, 1, 1. It's easy to calculate the complement of a set in this form. You just convert 1s to 0s and 0s to 1s. So this would correspond to the set 2, 3. Continuing, suppose we have a set that contains 1, 3, and 5, and another set that contains 1, 2, and 4. Notice that A is then represented by the bit string 1, 0, 1, 0, 1, whereas B is denoted by the bit string 1, 1, 0, 1, 0. So how do we calculate A union B? This is the OR statement, here or here. So if you have a 1 or here, so if you have a 1 in a position or a 1 in the other position, then it becomes a 1 in the union. And so the union would be the set 1, 2, 3, 4, 5. What about the intersection? They'll both have to be 1s to be included in the intersection. And so the intersection contains only this element 1. There's another concept called a multiset. These are like sets, but in this case, repeats do matter. So let's suppose I have the set that contains 1 and 1. That will not be the same thing as the set that contains 1 if this is a multiset. For sets, we do get equality. So we keep track of the repeats in multisets. So another example, suppose we have A, which is a multiset, and it has A, B, B. Two distinct elements, but they're repeats. And the number of repeats matters and makes a difference. One way of representing this is you get 3 of these A's and 2 of those B's. That might make it a little bit easier to write down. Generally, multisets are expressed like this: M1A1, 1, M2 times A2, Mn times A sub n. So we're telling you how many times A1 appears by putting in these numbers. The n sub k's are called multiplicities. It's easy to calculate the cardinality of such a multiset. All you have to do is count up the multiplicities. Unions and intersections work a little bit differently compared to sets for these multisets. The union of multisets includes the maximum multiplicity from either of the two sets. So, for example, if A is the multiset 3 times A, 2 times B, and B is the multiset 2 times A, 4 times B, then the union of these would be 3 times A, 4 times B. For intersections, take the minimum multiplicity, so in the example up here, we take the smaller of the two, 2 times A and 2 times B. How do you do set differences or multiset differences? Well, how do the multiplicities work? We'll have a multiplicity on A minus the multiplicity on B, but only if the multiplicity on A is greater than the multiplicity on B. And 0 otherwise. We can even define this concept for multisets, A plus B, and here you just add the multiplicities. In our next example, we're going to have several multisets here. We're going to have 3 times A, 1 times B, 4 times C, that's our set A, our multiset A. The multiset B will be 2 times A, 3 times B, and 2 times C. So the union takes the maximum of these multiplicities, 3A, 3B, and 4C. The intersection takes the minimum, so 2A, 1B, 2C. The difference, A minus B, well, 3 minus 2 is 1, 1A. You can't subtract 3 from 1, so I'll get 0 B's. And then 4 minus 2 is 2C. And finally, what about A plus B? Well, we'll have 5A, 4B, and 6C. We'll just add the multiplicities.